A distributed weight sits on one side of a beam, resting on a fulcrum at x equals 0. So this is the fulcrum right here. It's trying to balance everything. We get this weight here. And it says the distributed load has a weight density function given by that function. That's that equation right there, where A of x is measured in pounds per foot, x is measured in feet from the fulcrum. Where could a single 1,002.6 pound weight be placed in order to balance the beam on a fulcrum, on the fulcrum? Place a point at that location. So basically, we want to take 1,002.6 pounds and put it somewhere over here, maybe here, maybe here, maybe in the middle, maybe here, somewhere, and have it exactly balance all of this weight. How do you figure that out? Well, in class notes, choosing a point to bring balance on the fulcrum at x equals 0, calculate m0 first off the integral. Or if you have a point, if you have points, you do another formula, but we have a shape, we don't have points. So we're going to do this. So that's our first step. So m0 is the integral from a to b of x, rho of x, dx. So that's going to be the integral. A to b, we're going to go from, this is a, this is b, it looks like 3.5. They're going to make this, and they're going to, it's, you don't have to guess what that is. It's 3.5 exactly. So it's going to always be at a whole number or a half on this problem. So it must be 3.5 of x times this function, which is our density, that's our weight density function, minus 350x plus 1225 dx. That's going to give us the moment about the origin. It'll tell us, moments like torque, like the more weight, the further away it is from the center, the more it pulls down this way. And then we'll figure out what weight on this side will balance it. So, all right, so there's our integral. I'm going to go to Desmos graphing software, do the integral. I did already. There it is right here. And there's the answer. So I typed it in, just did that integral, and I got 2005.20833. 2005.20833. Good enough. 4 decibels is good enough. Okay. Now, what does that mean? That's the moment. That's MO. That's what MO equals that. So, okay, so what now? So now, given the weight W, so that's all step number one. Step number two, well, here, I'll do it over here. Step number two down here, the weight is right here, 1,002.6 pounds. Okay. Step three, solve this equation for x. So I'll do that over, I'll do it right here. Step three, so the equation, if you can see it right here, is MO plus X times W equals 0. It's basically a balancing equation. It's saying take your moment number, that'd be this number right here. I'll change the color here. So that'll be the 2005.20833 plus X times the weight, which is right here, equals 0. And that's basically saying it's going to bounce. Whatever this moment is, this shape produces a moment down this way, which is like a torque or it's a force at a distance. The further you put that same weight further away, it's gonna tend to be even stronger down, right? It's called a moment arm. So it produces a moment there, but we want to know if you add at what position X do we put the 1,002 pound weight, 1,002.6, so that it will exactly counter this whole triangle shape that's on the right side. Somewhere over here on the left, we're expecting a negative answer, right? So we're going to solve this equation for x. So you know how to do this. It should be easy for a Calc student, Calc 2 student. Jump that over there. So this will be x times 1,002.6 equals, when that jumps over there, it becomes negative 2005.20833. And last step, divide by 1,002.6. Boom. So x equals. Hit the buttons on the scientific calculator. Did I do that? I don't know if I did that. Let me see. Nope, I did not. Okay, so let me go back and do it again. What was it? It was negative 2005.2083, negative 2005, negative 5.20833 divided by 1002.6. 1002.6. 6 equals, see, I get negative 2 point with a bunch of O's. So it's basically negative 2. So, whoops, X is negative 2. So you should put that weight right there at negative 2. Use your, on the problem, you use a little device to put the right weight right there. That's right where the 1,002.6 pound weight should be placed. And if so, that'll make the moment on the left and the moment of this triangle on the right balance right at zero. The fulcrum at zero will be balanced perfectly if you place this 1,002.6 pound weight right at negative 2. So that's how we do that to bring balance in the moments.